And then I do exactly the same thing for species 2. So let's do it for species 2, again a random individual. So let the random individual be xi for the species 2. And let's say it's 0.1 and 0.2 negative. So I need to calculate the fitness function value of this individual now. I'll go extremely fast. So I need to calculate the fitness function value of this individual. So I need to say what is the fitness function value of this individual. So let's take rank 1 solution. So it's fitness of rank 1 solution minus the fitness function value, the ecosystem fitness function value of the rank 1 solution after substitution. So in that I'll substitute rank 1 for the species 2 with xi2. So this is what are the representatives. So what are the representatives? It's 0.8. Oops, the other way around. So let's do this thing again. So I need to calculate fi2. The ith individual from the species 2. So this is the fitness function ecosystem of the rank 1 individual with the substitution that the rank 1, the second species, is replaced by this individual. This time the representative of the second species was being challenged. So let's take the rank 1 individual. So it's still 0.8 minus 0.6 minus 0.7, 0.9. And in that I make the substitution. So rank 1 species 2. So this is rank 1 species 2. This is replaced by xi2. This is replaced by 0.1 minus 0.2. Minus the fitness of rank 1. So this is f of 0.8 minus 0.6 minus 0.7 and 0.9. So of course this will be 64, 36. Which becomes oops. So in this case, this individual is definitely significantly better than rank 1 individual. So now what I'll do is I'll just write down this fitness function value over here, minus 1.25 for the minimization problem, minus 1.25. And let's say the fitness function of all these was like this, random numbers. So the best fitness function value happens to be over here, which is of xi2. This gives me the best fitness function value for the minimization problem. It's minus 1.25, which is best amongst all of them. So now what happens is that I've got a better representative people. I've got a better representative. So the old representative was, let us say, this one. And now I've got a better representative, somebody whose value is definitely better than the current representative. So now what will happen is the representative will change, or the representative will become, and similarly I'll apply the genetic operators and making of a new population pool, which goes as usual without any change per se. So here it's an interesting algorithm. It's absolutely an inherently excellent algorithm. So you saw that two individuals or two species were cooperating with each other because the fitness function was used of the ecosystem. Nowhere did I use F1 or F2. I only use capital Fx. So I use only the fitness function of the entire ecosystem. So we were maintaining, in order to solve this problem, we were maintaining two population pool, one for this and one for this, but only this fitness function was used. That means an individual was not given a fitness function value based on its own goodness. It was given a better fitness function value upon how well it cooperates with a representative of the other individual, or with a representative of the other species. How well it cooperates with the representative of the other species to make the overall fitness function as good, to make the overall fitness function as something which is better. And that is the cooperative co-evolution algorithm. Now let me point out to one major flaw over here. So let's take the entire population, let's take the entire problem again. So we had a species 1 and we had a species 2. And we took in representatives. So this was the representative for species 2 and this was the representative for species 1. Now what if I take a bad representative? This representative is bad. It'll just not cooperate with anybody. And not only does it not cooperate with people, what it does is that the little cooperation it shows is with the wrong guys, with the wrong people. So sometimes what happens, bad representative, bad decisions. And that's exactly what will happen over here, that the population pool for this population is given a fitness function value only and only based on this representative, and this representative is bad, so the fitness function value can be misleading because of a bad representative. Eventually the representative will change, it will improve, but it's misleading. And therefore many times what you say is that instead of only taking a rank 1 representative, I go with multiple options. I take a rank 2 as well and I take a rank 3 as well. And similarly for species 1. So this is the rank. And this is the species number. And that's what I would have done with many people, of course. So sometimes you say that as a batch we are too diverse. We need 2 representatives instead of 1. So one representative will go good with certain kind of people, another one will go good with certain other kind of people. Many times you say that one representative is not enough, so you need more representative. But is there a trade-off? Yes, because now what I'll have to do is to calculate the fitness of any individual. Now to calculate the fitness of any one individual over the first population. Okay, I don't have a population. So now what happens is that there is a population pool also which goes like this. Now to calculate the fitness of this individual here, I don't need to just pair it up with rank 1. I need to pair it up with rank 2 and rank 3. So I need to do a lot of more computation. Every fitness function takes a lot of time. So I am tripling my time. I already doubled it up for 2 species because what in single fitness function evaluation could have been solved by just one fitness evaluation, the fitness function of the entire individual. Now, because I'm maintaining species 1 and species 2 separate, so the fitness functions are already doubled, and I make it 3 times over here, so my computation cost increases, but then I've got more options to choose from. So the individual which gives the best fitness function value with any one of the representative is the one that will be taken. So if you hate one representative, you can always go with the second one. You've got more options. If you hate the second, you can go with the third one up, but then my computation cost is increasing by a number of how many ranks do I take. So that is bad. And the other problem that it faces is that how do I decide which individual is rank 1, which is rank 2, and which is rank 3? How do I eventually go upon deciding that? Do I take the top fitness function, the second top fitness, the third top fitness? Yes, but then all your 3 representative may be exactly the same. So there's no way that it's going to increase the diversity in your representative, which is when you said that, yes, we are a democracy, we will elect our representative. There are 2 positions because we are diverse. So normally meant that people who are good in academics will be the first representative, people who are good in sports will be the second representative. But then election happened and everybody said, okay, who is the best? So 2 individuals good in academics got both the positions, rank 1, rank 2, and sports is not representative. So you get into the same problem over here. So now I'll solve in this problem by another algorithm. I'll try to solve this problem by another mechanism.